Okay, so let's get started again. The heat loss is really picking up. It seems to be getting even colder in here. I got to get out of here soon, so we'll try to finish up in next half hour. But now it's, I don't know if it's just me, but I feel colder now than the last hour. Okay. All right, so okay, now we talked about ignition devices like shock tubes, rapid compression machines. Good for measuring a global combustion phenomena. Also good to measure species formation, but species formation in a shock tube or rapid compression machine is done by lasers, okay? You cannot put a probe and sample the gas. It's very difficult to sample the gas from during the ignition process in a shock tube or a rapid compression machine. So it's usually done by lasers, and I'd say lasers today, you have about maybe 10, 15 species they can measure fairly well, because you need different laser wavelength for every types of species. So typically you see the things like for OH it's there, maybe CH, radical, methyl, there's good lasers. And then for stable species like some hydrocarbons, maybe ethane, propane, butane, alkenes, so maybe up to C5 alkenes, maybe some light aromatics. But you'll never measure like all the different aldehydes, ketones, and many other intermediates. Of course, you could do CO, CO2 very well. But again, more lasers, more expensive, more complicated. I think there was one paper at the 2012 symposium in Beijing from Stanford. It was this simultaneous measurement of like 6 species in a shock tube for heptane ignition. That was a lot. I mean, 6 lasers, around the shock tube. The lasers take up more space in the shock tube, all shining in there. It was pretty complicated. So, that's typically the limit. Maybe simultaneously, most people are doing 2 or 3 species. Doing 6 is very hard. So there's other experiments we like to use to measure species, because other configurations are then more amenable for speciation measurements during, say, low temperature oxidation, high temperature oxidation phenomena. One of them that's widely used is by Professor Dago at CNRS. He's the president of the Combustion Institute right now. He kind of pioneered the use of jet-stirred reactor for use for understanding combustion chemistry and kinetics. So this system is zero-dimensional also. It's something we call a perfectly stirred reactor in chemical engineering, or in chemical engineering we say continuously stirred tank reactor. It's a mixture that's perfectly mixed, but it's not a batch reactor. It's a continuous reactor. So the fuel continuously comes in to the reactor, it's mixed, and it exits, and it's also isothermal. So you fix the reactor temperature. So it's not like a shock tube or a rapid compression machine, which is non-isothermal, right? That starts out initial condition, initial temperature, then the reactions happen and the temperature rises and you have ignition. In a jet-stirred reactor, there's no ignition event. It's all isothermal. You control the temperature of the reactor. You minimize the exothermicity of the fuel by making sure there's less fuel in the reactant, and the entire reactor is placed inside of an oven, okay? So the key things that you need to note in these types of reactors are for JSRs, the initial conditions that matter are the temperature, of course, reactor temperature, which is isothermal, reactor pressure, the gas composition, so concentrations of reactants, and the last thing is tau, the residence time. how long does your gas mixture stay inside of the reactor? In the temperature and pressure of the reactor, okay? Residence time. And that's measured in usually seconds. Now the ranges of your reactor, typically the temperature can go, they can start at 500 Kelvin, and they can go up to about 1200 Kelvin. They can't really go beyond 1200 Kelvin because these things are made of quartz, maybe 1250. After that, the quartz starts melting, yeah, and becomes unstable, so you're limited by the material requirements, material constraints. Pressures are also, 1 to, typically 1 to 10, okay, is what you find for quartz jet-stirred reactors, but you have some people doing experiments up to 100 bar in high-pressure JSRs. Did you guys see one here at Princeton during the tour? Did they show it? Yeah? What is it made? I've never seen it. It's made of what, steel? Stainless steel, yeah. Professor Ju, right, his lab, they're doing supercritical jet-stirred reactor experiments, so very high pressure. I know the facility, they built it 5-6 years ago. I haven't had a chance to see it. But yeah, they can go up to what, 100, maybe even greater, greater than 100 bar. And residence times, we'll talk about this, how you get the residence time. They're typically between 0.1 to 4, maybe 3 seconds. That's the typical range you will see. Now, okay, so temperature is limited by your oven, because the whole thing goes inside of a furnace, limited by the materials. Pressure limited also by the material. Residence time, of course, it's something you can vary. How you determine the residence time is the whole point of the reactor is to be perfectly mixed or well mixed. And in chemical engineering, the way of determining well mixed is to make sure that the gas mixture has enough time to mix within the residence time of the experiment, okay? So typically we say that the residence time of a reactor is defined by the volume of the reactor, yeah, over Q, the flow rate of the gas. So the centimeters cubed divided by centimeter cubed per second, which is a volumetric flow rate, you get the global residence time of your reactor tau. So basically, this is how much time does the gas mixture spend in the reactor from the point it comes in to the time it goes out. And again, your standard way to determine if the mixture is well mixed is to do something called a residence time distribution measurement. And again, you might have seen these in different types of fluid mechanics courses as well. Tracer experiment. So what you do is you inject a tracer into the reactor, and then you monitor the concentration of that tracer in the exhaust. And if you could say the E of T is the concentration or the signal of measurement of your tracers, if it follows the form of 1 over tau exponential T over tau, then it can be represented as an ideal reactor, okay? This is the ideal equation for a perfectly mixed system. So whenever you design these types of jet-stirred reactors, you need to find out, okay, based on the volume of the reactor, the V, and the inlet flow rate of mixture components, what should be the flow rate condition to ensure that you have a residence time that is in the well-mixed regime? Because in the end, you need to model this as a well-mixed reactor. If the reactant gases are coming in too slowly, then it won't be well mixed. The gases will get in there, there'll be diffusion, there'll be gradients, and then they'll leave the reactor. Then it's not well mixed. If it's too fast, then also you can have things like too much collision against the walls and some turbulent mixing, and then you don't get the exact homogeneous mixture inside of the reactor. So what we do typically is we do these tracer experiments. You take your reactor with no gas, no reactant gases, and you inject a tracer, something like carbon dioxide or carbon monoxide, and you measure the concentration of that coming out, and you see, does it follow this ideal model, 1 over tau exponential T over tau, and you test different configurations of your JSR, yeah? So configure, like these are just different configurations. For example, configuration 3, the experiments do not agree with the ideal model, but configuration 5, configuration 3 operating in a different flow rate condition, so a residence time of 2.5 seconds does work well. So in this way, you identify what is the ideal residence time for your configuration, and then you make sure you do your experiments in this well-mixed regime. I think now what many people do is they just design the reactors in a CAD software, and then you do a CFD simulation. So it's a pretty straightforward non-reactive CFD. Then you just determine, you can do your residence time distribution experiment numerically. You inject a tracer in your numerical experiment based on the geometry, and you see based on what residence times are required to get into a well-mixed regime. So this is just a CAD drawing showing you what these reactors look like. So you have fuel coming in, you have an inlet regime where your fuel oxidizer and inert gas go in. They move into the spherical jet-stirred reactor through these nozzles. It might be easier to see. You see these nozzles are pointing in 4 different directions. One of them is pointing up, one of them is pointing to the left, one of them is pointing down, one of them is pointing to the back and to the right. So these create a lot of mixing as the gas comes in. It ensures that you have a well-mixed regime. The inner diameter of these is about 1.5 to 2 millimeters. So you got to make sure that the gas flow rate is not too large. If it's too large, you get a choked flow through these very tiny nozzles. That's not good. Also, if it's too large, you might get a shock wave because the gas velocity coming out of these very small nozzles is too large, entering into the larger volume. So you create some micro shocks which cause disturbances in the flow field. So you got to optimize your flow rate so you don't have, if it's not too large, and at the same time it's not too low so you don't have the well-mixed regime. And once you've designed your reactor, it's a pretty straightforward experiment to run then. Typically what's done is at the exit of the reactor, at this side, you simply flow your gas into a gas chromatograph or some other type of detection device. You don't use lasers in jet-stirred reactors. Because the entire thing is inside of an oven, there's no optical access. And even if there was optical access, it's straightforward enough to just measure the species using something like gas chromatography. So this is your reactor. This is the inlet. Let's say that's the inlet. So your reactant gas comes here. This is your exhaust. So your gases are coming in here. They're mixing, they're reacting, and they're going out. Typically what you have here is a probe made of quartz. And this is connected to a vacuum pump, okay? And then afterwards, this goes to a GC or some other type of diagnostic technique. So what you do is you don't really sample all the gas that's coming out. They sample it into a probe. This probe is connected to a vacuum, so the pressure here might be 1 bar. The pressure here might be 0.1 or 0.05 atmospheres, okay? And what that does is if you have a rapid pressure drop as the gas enters here, of course there's a gas expansion that cools the gas. So that freezes a lot of the chemical reactions. It freezes the species at the time of their sampling, so you ensure that there's no reactions happening inside of the sampling line, okay? So this drops the temperature. Right, this will drop the temperature down and drop the pressure down so you don't have any reactions inside, and basically freeze the species in time at the exit of the reactor. And then what you're measuring, you're measuring the mole fraction of different species as a function of reactor temperature. So this is the reactor temperature. So this is how this data would look. You have the fuel concentration. At low temperatures, the fuel is not consumed. As you increase the temperature, the fuel starts to be consumed. At around, in this case, 690 Kelvin, you reach a minimum in fuel concentration, but then it goes back up. That corresponds to that intermediate temperature reactive regime where different type of kinetic phenomena are slowing down the consumption of the fuel. And then you have the hot ignition or high temperature oxidation regime that consumes all the fuel. Now there's no per se ignition, but this high temperature region corresponds to the same types of reactions that are happening in ignition. Ignition is prevented in these types of reactors by making the fuel loading very low. So typically the fuel concentration will be less than, might be about 2,000 ppm, 2,000 parts per million. So the rest of the mixture is just inert gas and then a very little oxygen to get you the equivalence ratio that you want. So you minimize the amount of fuel so there's not much heat release, and therefore the reactor is isothermal because there's no heat release from the fuel, there's only heat from the oven, and the kinetics are then governed only by the chemical kinetics and the reaction kinetics at a fixed temperature regime. And what we see here, we call the hot ignition event, is not really an ignition, it's just a high temperature oxidation which is measured by the change in species concentrations. So again, low temperature oxidation, intermediate temperature oxidation, the NTC region, and high temperature. And then you have the formation of things like ethylene. Ethylene is formed as the fuel is consumed, but then ethylene is also consumed because this is an intermediate species, it's not a stable product species. Hydrogen is also produced, and then hydrogen is consumed, and eventually, again, where in the low temperature region, you made things like CO, CO2, and water, and then they're produced more in the high temperature region, and eventually at the end, above 1100 Kelvin, see all your ethylene, all your hydrogen goes down to zero, and then you start only make things like CO2, water, and carbon monoxide, some carbon monoxide. Not all the carbon monoxide will be converted to CO2 because one, the residence time is usually not long enough for CO to be converted to CO2, and also the temperatures are not high enough. Typically, CO to CO2 conversion, you need to get to about 1300 to 1400 Kelvin. So it's a snapshot, okay? It's a snapshot in time, in temperature of some of the reactions, and we use this then to understand much more about the chemistry. So phenomena we typically look at are high temperature oxidation, intermediate species that are formed, but also nowadays, JSRs are used a lot to measure a lot of the species that are formed in this cool flame regime, the intermediate temperature regime. And so a lot of the interesting kinetics we have around low temperature oxidation are being developed because people are identifying interesting new species inside of jet-stirred reactors in this regime. And similarly, the supercritical jet-stirred reactor, like this one's that operate at 100 atmospheres, very interesting because no one's done these experiments before. So now they're starting to look at, okay, in very high pressures, I think they're just, for now, using rather simple fuels, but looking at different species that are formed at very high pressures, and can you get models to predict those types of kinetic phenomena. Okay, another commonly used reactor for speciation are flames. So of course, flames can be used for flame speeds and extinction and ignition. I'll talk about that. But first, we can even use flames to measure species. So this is a premixed burner stabilized flame. Somebody before said they were doing burner stabilized. Well, what are you doing it for? And what pressure? Atmosphere. Are you measuring species? Yes. So he says he's doing atmospheric ammonia flames measuring species, burner stabilized flames. And okay, so, and what do you use to measure the species?
We're doing this.
Optical emission spectroscopy. He's using absorption spectroscopy. Okay. So he's using absorption spectroscopy, so laser, yeah, to measure the species. So that's interesting. We'll talk about I think it makes sense to use a laser under some conditions. Others, doesn't make sense. Okay? So a premixed burner stabilized flame is shown there up above. I think I drew it earlier. You have some kind of a burner. This burner I show here is a McKenna burner. It's just a porous burner. So you have a sintered metal matrix through which the gas flows. And the gas is flowing, in this case, to the right. And you ignite the flame. Okay, you ignite the flame at some point, and it gets stabilized on the burner. This might be our flame here, okay? The fuel and oxidizer are coming here. The phi is fixed. The initial temperature is fixed. The initial pressure is fixed. And of course, because you have a flame, now you have exothermicity from the flame, so then you have temperature gradients along this direction. So the temperature should be rising as you go into the flame. Species will be consumed like the fuel and the oxidizer. Intermediates will be formed. And there's a lot of interesting things that can be observed. So you have a preheat zone. That's where the fuel starts breaking down. You have the flame. You have the main reaction zone where all the major intermediates are formed and where they're consumed. And then you have the post-flame zone where you have your products being formed. And all of this, you look at distance above the burner, or distance away from the burner. And the things they try to measure in these, you're trying to measure typically the mole fraction of different species, but also the temperature profile. So first, how do we measure? If you see this one, flames, many people do these flames at low pressure, 10 to 100 torr. So say 1/10 of an atmosphere or so, yeah, or less. And our colleague here says he does it at 1 atmosphere. Well, there's a reason some people do these things at low pressure. And the reason is many people who do this type of low pressure flame experiment to measure species are using a probe. They're using a cone or a probe, which is connected to, again, a vacuum pump. And then usually some kind of mass spectrometer, MS, or maybe a GC or some kind, okay? Now, one thing happens at low pressure, reactions are slower, right? And gas density is lower. So the flame thickness increases at low pressure. So first of all, your flame stands off distance from the burner, DAB, let's say. DAB, not dad, okay. Dad, okay, distance above burner or distance away from burner. That distance increases. And also your flame thickness will be broader, okay? Your flame will be broader as you go to lower pressures. So one advantage of doing this experiment at low pressure is you can get more resolution in distance of these different curves. These different curves, right? Like temperature, species concentration, they'll become broader. At high pressure, 1 atmosphere, these things must be very narrow. And the flame will sit much closer to the burner surface. Now, if you have a probe, this probe is a physical thing. It has some dimensions to it. The orifice might be 200 microns. So if you're trying to sample species, the physical probe is somewhat of a barrier, yeah? And if your flame is too small, too close to the surface, you won't be able to even resolve anything. Your resolution might be like 500 micron. If your burner sits 1 millimeter away from the surface, you might only get 2 measurement points or something. So because of the physical barriers or the obstruction of this cone, this quartz device that's doing the sampling, you prefer to do it low pressure. Now, he wants to do it at atmospheric pressure because he has a laser. And a laser has a very good resolution. I don't know, what's the resolution on a laser?
Let's see, measurements every eighth of a millimeter.
Eighth of a millimeter, okay. So that's pretty good, a few hundred micron, right? So it's a very much better resolve than a cone. So even if the flame sits nearer to the burner, you can do it at atmospheric pressure. Much easier to do an experiment at atmospheric pressure than at low pressure. These experiments, you got to put the whole burner inside of a vacuum chamber and then suck out the gas continuously as you pump in the gas. They're pretty, I've worked on this at Lawrence Berkeley National Lab. We've done these experiments. So the burner sits inside of a vacuum chamber. You have turbo pumps to drop down the pressure. You have this probe sampling, which also has to sit inside of the vacuum chamber. I mean, it's a big experiment. And if something breaks inside, like you translate this cone, okay? This cone is connected to some kind of a motor. So it can move towards and away from the burner surface. And if you move it too close, like I've done many times, you break the cone. Yeah, then what you do, if you break the cone, you gotta rip apart the entire rig, depressurize it, or repressurize it, take it apart, change the cone, and you lost 1 day of experiments. And we do these experiments at the Advanced Light Source in Berkeley, where you have, I'll show you in the next slide, a mass spectrometer that's capable of resolving many species. Well, they only give you like 4 days every year, and if you waste 1 day because you broke the cone, then your professor is not happy with you. So that's why these experiments are very good. Again, leading groups are like Niels Hansen at Sandia National Lab, groups in China at Hefei, in Germany, Bielefeld, Katharina Koscher-Horinghaus, she was the previous president of the Combustion Institute. She did many experiments in these types of things. But again, if you do it at atmospheric pressure, you don't have these chambers. You just do it in your room, outside. You have a laser. You can resolve the space. It's different. So again, different depending on the diagnostic tools that are available to you, you will do your experiment in different ways. There's a problem with these experiments. Again, the combustion community did a lot of these experiments from like 2000 to about 2015. Many papers published in the symposiums, and we use them a lot for kinetic models validation because you can measure many species at the same time with these probes. So you can measure like hydrogen, oxygen, water. You can measure all the intermediate species because we use very advanced mass spectrometers. So in one experiment, you might measure like 90 to 100 species. It's amazing. Yeah. Even you can measure radicals because this cone is connected to a vacuum. And so if this is, as we said, 0.1 atmospheres flame, this one would be like 0.01 atmospheres. So maybe 10 torr or something. So extremely low pressure inside of the probe. And then it's sent to a mass spec that's like 10 to the minus 4 to 5 atmospheres. Extremely low pressures. We call this molecular beam mass spectrometry, MBMS. I don't know if I've written it here. MBMS, okay? That stands for molecular beam. Mass spectrometry. Molecular beam mass spec. Group here at Princeton also does it. Jules' group has done these experiments at the light source. Because this gas enters into the probe, its pressure drop is so fast and so large that it enters into the mass spec. Another pressure drop. The molecules go from something like a standard gas dynamic regime into a free molecular flow. The distance between the molecules becomes so large because of these low pressures, and you get a free molecular flow. Radicals are basically stabilized. They don't see anything else to collide with and to react. So you can actually measure radicals like CH3, C2H5. And so this became really nice. I mean, never before could you validate a kinetic model against radical intermediates because you're never able to measure them. But these types of experiments enabled you to measure radicals because of this very, say, elegant sampling technique, molecular beam mass spectrometry. Okay, but it comes with its drawbacks. Okay, the drawback is you have this massive cone, which is almost the size of your flame. And what do you think that does? Huh? Okay, one is heat. It's a massive heat sink. Yeah? And so you no longer know the temperature in your system, and a kinetic controlled regime, a kinetic experiment you need to know the experiment. So a burner stabilized flame with a laser, I don't have to worry about that, right? Because as long as I know the temperature of the surface and you know the chemistry, you can easily model the heat loss to the surface. But modeling the heat loss to a cone like that, you have no idea what the temperature of the cone is. It's changing as it's moving throughout the flame. So it became very difficult to really understand what your temperature is. And in the end, what's really happening is the gas that you're sampling is not really at the temperature that you think it is because of the cone. So it's at some lower temperature. So if you simulate this, you cannot simulate the cone. It's a body of the experiment, which is very difficult. You would need to do a full CFD. People have done DNS simulations of it, and they've shown that, yes, it has a major effect on the flame. It has a major effect on the temperature. But we're doing kinetic models. We just want to model this as a very simple premixed burner stabilized flame. We neglect it. Yeah, you will be assuming the temperature is higher than it really is. And that's let's say, an artifact of the experiment. How do we deal with that? Well, these guys are pretty clever, okay? They put a tracer molecule inside of the gas mixture. So they feed this mixture with argon, or sometimes helium, that comes in. And these are inerts. Now, as this gas goes in, it's not reacting, but they can, as a function of the temperature of the gas, will determine how much gas enters into this probe, because the temperature of the gas, and depending on gas kinetic theory, you can say the temperature of this molecule, because we know all the different states of this molecule at different temperatures. As it enters a probe crossing a specific pressure drop, we should know exactly the amount of gas that could be sampled. And that's purely physics. There's nothing to do with chemistry there. And then they measure that with the mass spec. And then from the mass spec, they can back out what was the temperature of the gas that entered into the mass spec. And then they provide us this information. And that helped. It was like it had about 50 to 100 Kelvin error, which is not bad. Okay, you deal with it. And then you got to do things like shift your profiles, or in your paper you explain. My profile doesn't exactly match the experiment because we know there's this 50 to 75 Kelvin error, but it's better than not knowing any temperature at all. Okay, so those are these kinds of flames, very nice flames, nice experiments. Maybe the last thing we'll look at is the low pressure. This is a wrong heading here, I'm sorry. This is a premixed laminar flame speed vessel. Okay, premixed laminar flame. You must have seen this also when you went through the labs at Princeton. This is a different configuration. This is for measuring flame speeds, so not for measuring speciation. So here they just take a chamber, and inside of the chamber you put fuel air mixture, and then the chamber has some windows, so you can do diagnostics. I think in this case, they can do simple things like Schlieren imaging. And then the gas mixture is ignited with a spark. And then you have what we call a spherically propagating flame. Yeah? And that's how you measure the flame speed, is in these types of chambers. And of course, Professor Law here at Princeton has published many papers on flame speeds and different types of devices. Professor Ju also has them for measuring the laminar flame speed. Spherical vessel, fill it up with fuel and air, ignite, and the flame will propagate like a balloon, yeah, expanding balloon. Of course, there's lots of physics involved with that expansion. if this chamber is sparked in the middle and you have a flame, the flame is initially very nice and round and growing, but as the flame gets bigger, you start to have wrinkling, yeah, and then eventually it might look very, very awkward. Anybody remember what we call these things? When the flame sheet starts getting wrinkled, has Professor Pitch covered it yet? Or you might have learned in your classes? Somebody must know, come on. Huh? Cellular instabilities as a result of? What causes these types of instabilities? Huh? Turbulence. Well, there's not necessarily mixing here. Yeah. Okay, stretch-induced instability. Hydrodynamic. This is all, yeah, mainly hydrodynamic instability. Yeah. So, and once this starts happening, hydrodynamic instabilities, the flame is no longer smooth. You don't know where the flame surface is. So, in order to measure the flame speed, they need a very nice round flame. Okay. And that round flame is usually not at the very beginning, because at the very beginning the spark creates a wrinkled flame structure. The flame starts growing. It's nice and smooth. And then they try to look with the camera. They try to track this flame surface as it grows. Yeah? And it has to be done in only a specific period of the experiment. Because if the flame gets too large, then you get all these hydrodynamic instabilities. You can no longer track the flame front. And the flame speed is basically, yeah, the propagation of this flame front as a function of time. And that's a fundamental property of the kinetics of the system. And it has to be done under laminar conditions. It has to be done freely propagating with no other things like instabilities coming into the play. At the same time, though, if you look at this curve, who's measuring flame speeds here? Anybody? You are? In what device? Huh? Constant volume? Okay, he's doing a constant volume chamber. Where's that at? West Virginia? Okay, and you use Schlieren imaging or what? You use Schlieren imaging, which is looking at the density gradient to measure the flame. So you'll be measuring the flame. Do you look at the stretch effect?
Yes.
Okay, can you tell us about it?
So the stretch is defined by the curvature and strain. And that's going to affect propagation rate is
Okay. Yeah, I mean, okay, he explains it very well. I hope everybody can read that or hear that. So he's saying that, okay, the flame is being stretched, and as a result of this stretch, the surface area of the flame changes, and that influences the propagation rate. And this is a physical phenomenon, a physical effect. It's not a kinetic phenomenon, right? And again, our goal is for true laminar flame speed, by definition, is the speed of a flame in the absence of stretch, under zero stretch. That's the definition of laminar flame speed. Now, in reality, there's no system in the world where you can actually observe a flame under zero stretch. Actually, you can in microgravity. So you got to do your experiment on the space station, yeah? So, and that's, yeah, people do that. We send experiments up to the space station and we measure flame speeds. But that happens once every 5 years. And again, the experiment doesn't always work up there, right? So yeah, basically, this is the stretch rate here, or strain rate, and this could be the flame speed. And what happens is you have some flame speeds at high stretch. Okay, this is just pictorial. Don't take these plots as exact, okay? So what happens here is you have the flame speed increases as there's more stretch, but then as there's less stretch, the flame speed starts slowing down. There's even people show that, okay, sometimes at low stretch, the flame speed goes up again, and then it comes down. And eventually, you're trying to get to this point of zero stretch, which is the point you can't measure, right? So they always try to find some fitting of where does the flame speed cross the y-axis, yeah? Or the x-axis at zero stretch. And that has to be done using some mathematical correlation, yeah? They basically take these points just before zero stretch, the nearest points they can measure, and they fit a line, and sometimes they fit that linear, they just make a linear correlation, and then for many years people fit a linear correlation, and they extrapolate to zero stretch, and they said, this is the flame speed at zero stretch. Then Professor Law and some others said, no, it's not linear, there's a non-linear correlation because you have some kind of bump here. So you need a non-linear function. And we used to go to meetings, and the guys would always just be arguing, is it linear or is it non-linear? Is it linear or non-linear? And people don't like the non-linear because it's too hard. And the linear guys say, we like the linear function. And yeah, you would have, the good part about combustion community, we have a lot of characters, okay? And these characters, they get really heated about very small details in their experiments. So you'd have big fights at combustion symposium just about this in like the laminar flame colloquium. Now the laminar flame colloquium is pretty boring because I think everybody agreed, okay, let's just use nonlinear, and they moved ahead. So they come to this point, they identify a function to extrapolate to zero stretch, and they say, okay, this is what we're going to take. And then you get these kinds of plots, laminar flame speeds. So this is, again, two different fuels, N-octane and 2-methylheptane in air. N-octane is the red, I've not noted it correctly, and 2-methylheptane is the blue. You see 2-methylheptane has a lower flame speed because it has a branch compared to N-octane. And they get these flame speeds at different equivalence ratios. And you see here the temperature and the pressure. One of the issues with flame speed measurements is that they're always around 1 atmosphere, maybe 5 atmospheres or 10 atmospheres here. This is some work done here at Princeton, 1 bar, 2 bar, 5 bar. It's very hard to get experiments done above 5 bar, maybe 10 bar at best, because the issue is once you go to high pressure, of course, the flame achieves instability much sooner, so you don't have a very good region where you have this nice smooth flame surface to track, so you can't measure the flame speed so well. And then also the issue is temperature. Typically they only go to like room temperature, maybe 350 Kelvin or 400 Kelvin at most, 100 degrees C. But flames propagating in engines are like at 30 bar and 800, 900, 1,000 degrees Kelvin. So the flame speed, we use it to validate kinetic models, but we really don't know. Are our kinetic models accurate for flame speeds at high temperatures and high pressures in real combustion environments? Because no one's been able to measure this. And this is a challenge we have. We extrapolate currently. We don't know if our models are even correct. But we trust that they are, yeah? Okay, so yeah, I think there's a group in India, Kumar's group in Mumbai. They do some measurements up to like 500 degrees C, but very, very challenging to get it done. You got to heat your mixtures a lot. Let's end it there before we all freeze to death, and see you tomorrow.